Have you ever experienced a situation like this? Suppose you just requested a ride on the ride-hailing app, and just in the blink of an eye, you are matched with the driver. However, the driver is too far away from you. Then you keep waiting and waiting for the driver to pick you up. It can be more upsetting, especially when you are in a rush. What could go wrong? 1. The driver supply in the vicinity is probably low. 2. The matching time interval is too short. With these two factors combined, drivers are so sparse, then the pickup distance is unexpectedly long. Yes, extending the matching time interval could save the trip. In this numerical example, drivers in yellow and riders in black are matched every 1, 10, and 30 seconds. The matching pair is collected with a green line. The pickup distance of the 1-second matching is obviously longer than the 30-second version. Undoubtedly, the average total wait time of the 30-second matching is the shortest among the three. Is 30 seconds the optimal matching time interval? It depends. So let me explain how we determine the optimal matching time interval while you are waiting for your driver. In a generalized queuing model, we observe that the matching wait time increases linearly as we delay the matching, while the pickup wait time drops sharply. The optimal matching delay lies in between. If we plot the optimal delay for various supply and demand combinations, the delay needs to be long enough when the supply nears demand. In a nutshell, delayed matching matters, especially when supply and demand are low and close. In the real world, the supply and demand patterns are more complex. They are stochastic in time and space, and also intertwined with matching decision process. The system dynamics, which are required for Markov decision process, are therefore unknown. We choose reinforcement learning as a remedy to this challenge, since it can approximate the dynamics by sampling the decision process. Nevertheless, 3 more challenges need our attention. 1. Large state space. The state space will be prohibitively large if it contains all relevant information. Inspired by the previous analytical results, we abstract 4 aggregated variables as partial observations. 2. Sparse reward issue. Rewards appear only when a matching is made, otherwise they are always 0. This sparsity can hinder the learning performance. By observation of the matching process, we propose a reward decomposition to spread the one-shot rewards over training steps. 3. Learning inefficiency. Traditional value-based RL methods, such as Q-learning, are inefficient in sampling. We instead choose 2 policy grading algorithms and modify them for faster learning convergence. Then we test our algorithms in a simulation driven by a Shanghai taxi dataset. We can see the supply and demand vary drastically in space. We therefore partition the area into 3x2 grids. The algorithm will decide whether to match for each grid. Specifically, our proposed algorithms include ActorCritic and its upgrade with Experience Replay. We benchmark them against instantaneous matching and fixed interval matching. We use LabSolver to solve the intensive bipartite matching and step baselines to train the algorithms. The learned policy can reduce the total wait time by 28%, which is higher than previous results. It's worth noting that our model has only 1 agent, which has a significantly smaller state space that makes the learning more computation and memory efficient. Additionally, we're interested in how the learned optimal policy works. We have 3 observations. First, delayed matching is in place when number of passengers and drivers are close to each other. Second, whereas the delay is shorter in a region with higher demand. Third, instantaneous matching is in place once driver supply exceeds passenger demand. In a nutshell, the NERD policy is found able to incorporate the trade-off principles into matching decision-making. To summarize, we uncover the trade-off principles between matching wait time and pickup wait time. We propose modified reinforcement learning algorithms to tackle 4 major challenges to the ride-hailing matching optimization problem. We find the optimal policy that exhibits a remarkable performance improvement in numerical experiments. We interpret the policy visually and find the NERD policy has successfully incorporated the trade-off principles in the decision-making framework.